Next is the theorem. It says the total number of edges of a complete, remember a complete graph, Kn is given by this equation, which is n is the size of the graph, number of vertices, is equal to n times n minus 1 over 2. Now, how to deduce this equation? Here is the proof, and it's going to be direct to proof. First, we will say let G be a graph with n vertices, and give them labels V1, comma, V2, up to Vn. Then the degree equation, which is summation, I goes from 1 up to n degree of V, is equal to degree of the first vertex plus degree of the second vertex until the last vertex of the degree is Vn. Now, since it is complete graph, then every vertex is adjacent to all other vertices. So the degree for each of them is the same fixed. If the size of the graph is n, so every vertex is not allowed to have loops and parallel edges, then the degree for each of them will be equal to n minus 1. And for the next one is n minus 1. So all of them are of degree n minus 1, and the size or the number of these vertices, so this equation is added. How many times? It is added n times. And now, since you are adding n minus 1 n times, then this is equal to n times n minus 1. And remember that this equation is equal to twice number of edges. From this equation now, we can deduce, or we can say that the number of edges is equal to n times n minus 1 over 2, and this is what we are looking for as a proof. For the last example, let G be a graph in which all vertices have degree at least 2. So the degree for each vertex is at least 2. Then prove that G contains a cycle. Now for the proof, we will first consider if the graph has a loop, then it has a cycle of length 1. And if it has parallel edges, then it has a cycle of length 2. And this verifies that the graph has cycle. So let us say that if G has a loop, then it contains a cycle of length 1, and if G contains parallel edges, then it contains a cycle of length 2. So in this case, we will assume that G, so we may assume that G is simple. Okay? So we will assume that there are no loops and no parallel edges. Now, how we will approach the proof? First, I will explain it to you in a draft, and then I will write the proof. Now, since every vertex of degree at least 2, imagine the following situation. Here we have a vertex, here we have a vertex, and a vertex, and etc. Now, if you want to make sure that all of these vertices minimum of degree 2, then you can form a cycle like the following. So to guarantee that each of them of the vertices of degree 2, see this is degree 2, this is degree 2, 2 and 2, and it is possible of degree more than 2. But for the minimum, if minimum is 2, if for the minimum we have a cycle, then for any degree greater than 2, there will be a cycle. So this is now degree 2, this is degree 2, this is degree 2, and assume that we are covering all vertices. So no vertex of a graph is left outside. So we will put them like in a chain, and we will call it longest path. Longest path. So the sequence of vertices we are visiting is like we're taking a path. So now this one is degree 2. This one is degree 2. This is degree 2, degree 2. Now for this one. Now for this one, since all vertices are covered in this path, now for this vertex, I need to connect it with other vertex. And also for this one, I need to connect it with other vertex. Now let's consider this one as an example. Now if you make it adjacent with this vertex, then this is a cycle. And if you make it adjacent to this vertex, also you have a cycle. If you make it adjacent to this vertex, also you have a cycle. So any choice of any other vertex, you will form a cycle, and this is the idea of the proof. So let us write this in the proof. Let P equal to V0, V1, and it goes to Vk minus 1 and goes to Vk, B, the longest or a longest path in G Now, because the degree of Vk, which is the last one, okay, is at least 2, it has a neighbor V different from Vk minus 1. Let me show you the picture of this path. So here you have V0, this is V1, this is V2, and you keep going until you reach Vk minus 1, and this Vk minus 1 is adjacent to Vk. Now here it says, what I'm saying here is that because of the degree of Vk, which is the last one, is at least 2, so it has a neighbor which is V, and I'm going to write it here in different color. So we will have a neighbor which is V, different from Vk minus 1. Why different from Vk minus 1? Because if you have an edge that going back, then this is a parallel edge, and we have excluded parallel edges. So what is a candidate for this vertex V? And here what we are going to write here. If this V is not on P, which is the longest path, then P contradicts the choice of P as a longest path. As we mentioned, that this path should include all vertices. So if this V is not on the path, simply include it on the path to make it the longest path. Therefore, V will be equal to Vi. And what are the candidates for Vi? The candidates for Vi will be any vertex for I, V0 up to K minus 2, and V0, V1 vk minus 1 and vk is a cycle in G. Maybe I need to elaborate more about what I am writing here, because if you remember that in the picture, we said that if V is not on the path, just simply add it. But if it is already on the path, then it should be adjacent to which vertex? It can be adjacent to V0, it can be adjacent to V1, V2, and it can be adjacent to Vk minus 2. For all cases, V0, the path, is forming a cycle. So this is the diagram. So what are the candidates for V as an adjacent? Okay, because we said that Vk should be adjacent to a vertex V. So what are the candidates for V? The candidates for V is either this vertex, which is V0, or V1, or we keep going and see Vk cannot be adjacent to Vk minus 1, but it can be adjacent to Vk minus 2. So the last value will be here as Vk minus 2. So we can say that I is bounded between 0 and k minus 2 and we remove this, all these vertices, and we simply that this is equal to Vi. And what is the value of Vi? The value of Vi will be in this interval. And this will complete the proof of the graph, that if we have a graph such that every vertex of degree at least 2, then there must be a cycle in the graph.